Good day, good people. Let us look at this cantilever here. Right. Um, when you are given the cantilever like this, the first thing that you need to do is to convert your UDL into a concentrated load. That is the first thing that you need to do. Why? So that I can be able to calculate this reactional support. Now we are given a reactional support on the free end. We then have to determine the value of that force there on the free end. Now, in converting the UDL in being a concentrated load, it will be 6 Newton per meter multiplied by the displacement there, it is 4. Then I get my answer is 24 Newton. Now, after you've converted this UDL into a concentrated load, you will put it at the center of that distance. Why the center? It is to indicate that you still have what? The UDL from this point. Let's denote this one as A, this one as B, this one as C and D. It's just to indicate that from point A to B, you still have what? The uniformly distributed load. Okay. Now, the second thing that you will do, you will then take moment at D. In taking moment at D, you are determining that reactional support there. You will say take moment at D. When you take moment, you will then determine the forces which are rotating clockwise and the forces which are rotating anti-clockwise. You will then say sum of the clockwise forces equals to sum of the anti-clockwise forces. If this is where I have taken moment, I will then be able to determine. Remember, for you to be able to determine, you must always work towards where you have taken moment. For instance, if I'm looking at this force working towards where I've taken moment, you can tell that the direction of this force, it is what? It is clockwise. Then I'm having 5 multiplied by perpendicular distance, and perpendicular distance, it is 1. Plus, I'm having 24. If I were to move towards where I've taken moment, you can tell that the motion, the direction of that force, it is what? It is clockwise. Then it will be 24 multiplied by perpendicular distance. The distance would be 4 plus 2, that would be 6, equals to the only anti-clockwise that I have, it is at A, the reactional support, the unknown that I'm looking for. It's when I move towards where I've taken moment, you can tell that the direction, it is anti-clockwise. Then it will be RA multiplied by perpendicular distance from here to there. It is what? It is 6. Now here it can be 6. It is what? It is 2. Remember, after you've placed that at the center, it is 2. Now it will be 2 4. Here it has to be 4, not 6. Sorry about it, good people. Right, it has to be 4, not 6. Now we are having 24 multiplied by 4 equals to 96 plus 5 equals to 101. Now when I remove the bracket, add multiply this side, then I get my answer as 101 equals to 6 RA. Therefore, RA would be 101 divided by 6. Then I get my answer as 16. Get my answer is 16,833 Newton. That means the force at RA, it is 16,833 Newton. Now, in determining the force on the fixed point, remember on the fixed point, you are having an upward force there. Don't forget that. Now, in determining that upward force there, I will then say sum of the upward forces equals to sum of the downward forces. Now, force fixed or force D equals to 5 plus 24 minus the calculated one, 16,833. Then I get my answer as 29 minus 16,833. Get my answer as 12,133. I've now determined the force on the fixed point, and the force on the fixed point, it is 12,133 Newton. When you add the two, you must get 29. 16,833 plus 12,133. I get my answer as 29. Did I call it? It's 29 minus 16,833. The answer here it's supposed to be 12,167 Newton. I don't know where am I taking 133. It is 167 Newton. Right. Because when you add the two, 16,833 plus 12,167 equals to 29. They must give you 29 equals to 29, then our beam is balanced. Right, this is how you work out your reactional supports on your cantilever. Now, even if you can say take moment at RA and consider this as an upward force, you will still get the 12, because if I've taken moment at RA, now it will be 24 multiplied by the forces which are rotating anti-clockwise. It will be 24 multiplied by 2 plus 5 multiplied by 5 equals to the only force rotating clockwise. It will be this upward force there. If you were to repeat this process twice, taking moment at RA, then it will be equals to F fixed multiplied by the perpendicular distance from there to there. It is 6. Then it will be FD equals to 25 plus 48 equals to 73. 73 divided by 6, you get your answer as 12,167 Newton. Now, either way, it doesn't matter. Whether you want to take this route or that route, when coming to cantilever, you will be marked correct. Then from there, let's wipe so as to be able to draw the shear force diagram. We've managed to calculate the two unknown forces. We now know that on the right hand side of that cantilever, we need 16,833 force. Then on the fixed point, we need the force of 12,167. Now we said it that on all given forces, we then have to draw vertical straight lines. On all given forces, let me wipe here and write nicely. Said it that on all given forces, D, this is D, it is 12,167. RA, it is 16,833 Newton. A, B, C, D. Then here it was the force that we got here. It is 24. Right. We said when coming to the shear force and the bending moment, on all given forces, we will draw the vertical straight line. You start on the fixed point, you draw the vertical straight line. Okay, then you come on the 5, it's given force, we draw the vertical straight line. Where the uniformly distributed load starts and ends, you draw the vertical straight line as well, because the effect of this extra load, it is from this point to from B to C. Now you need to write the vertical straight line as well, where it starts and ends. draw the vertical straight line. Then we'll replicate that beam as a horizontal straight line. Remember, we need to start at 0 and end at 0. We need to start at 0 and end at 0. Now, we said it that when coming to the cantilever, it doesn't matter whether we start at the free end or fixed point, your shear force diagram will be correct. Now, in this case, we will start at the fixed point. I will represent that as 12 comma something. Please, it's not up to scalar. This would be 12 comma, right, this would be 12 comma 167. It's a positive force. It's going up. It is what? It is positive. Okay. Now, between D and C, there's nothing there. There's no extra load on top of the beam. I will then represent that force as a horizontal straight line. Okay. Then it is 12,167 minus, on this line I'm having a downward force. Now it will be 12,167 minus 5. Then I get my answer 7,167. There it is there. Boom. It is 12,167. Now, let's write it a bit. Yeah, somewhere there is. Now, between C and B, there's nothing there. There's no extra load, nothing. We'll then represent that force as a horizontal straight line. Right. Now, between this point B and point A, there's a downward force there. And remember, we are having 7,167 minus downward force. It's going down. It's a minus 24. Then I get my answer as negative 16. Can I represent my negative 16 as somewhere there? Boom. Right. Then on this line, I'm having an upward force. It is 16,836. Now, 16,833, of which it is negative, plus that one equals to what? To 0. We started at 0. We ended at what? At 0. Now, let's go ahead and write our values there. Let's use the black one. Here we had 12,167. Okay, to here 12, it's a positive one. Right. It is 12,167. Then we said minus 5. Then on this point we got 7,167 to this point, 7,167. Then from this point we said minus 24. Then on this point, when we minus, we got negative 16,833. Then on this line we are having the upward force. Then this plus that equals to 0. Then equals to what? To 0. We started at 0. We ended at 0. Now please make note, where shear force equals to 0, it's the indication. No, here it's not applicable, that statement, that it is the indication of the maximum bending moment. No, it's not applicable, because our maximum bending moment, it is on the fixed point. It's on the fixed point. Don't forget that. Okay, let's replicate our beam. There it is. in drawing the bending moment graph. We need to start at 0 and end at 0. This, it is not applicable. Shear force equals to 0. Indication of the maximum bending moment, it's not applicable. Our maximum bending moment on the cantilever, it is always on the fixed point. Now, bending moment at A, and we said it that when coming to bending moment, we start from free end, we work towards the fixed point. Now, bending moment at A equals to 0 Newton meter. Then bending moment at B, on that point, it will be 16,833 multiply by perpendicular distance, of which it is 4, plus open bracket, negative 24 multiplied by perpendicular distance. The perpendicular distance, it is 2, equals to 16,833 multiplied by 4 plus negative 24 multiplied by 2. I get my answer on the bending moment as at B as 19,332 Newton meter. Then bending moment at C equals to, bending moment at C, we are having 16,833 multiplied by perpendicular distance from here to there, it is 5, plus negative 24 multiplied by perpendicular distance, it will be 2 plus 3 plus 1. 2 plus 1 equals to 3. Then I get my bending moment at C. It is 16,833 multiplied by 5 plus negative 24 multiplied by 3. Then I get my answer at C as 12,165 Newton meter. Then bending moment at D. Bending moment at D, that's our fixed point. Bending moment at D, it will be negative 5 multiplied by 1 plus negative 24 multiplied by 4 plus RA, it's an upward force, it's a positive one, 16,833 multiplied by 6 equals to negative 24 multiplied by 4 plus 16,833 multiplied by 6. I get my answer, bending moment at D, as negative 0,002 Newton meter. That's what I get there. Bending moment at what? At D. And that's our maximum bending moment, by the way. Right. Because we can't say this is where shear force it is 0, it is the indication of our maximum bending moment. We can't. Not unless they want us to calculate the bending moment where shear force it is 0. Now, if we were to calculate the bending moment where shear force it is 0, it will be bending moment, shear force equals to 0. Then it is going to be, we then need to get the distance from here to there. In getting the distance from there to there, it is going to be this force here, 16,833 divided by the value of UDL, it is 6. Then we get the distance there as 16,833 divided by 6. as 2,81 meters. Then we can then calculate. Now, if we take moment here, if we take moment there, then it will be 6 multiplied by 2,81 multiplied by 2,81 divided by 2, close bracket, plus 16,833 multiplied by distance 2,81. Then I get my answer as negative 6 times 2,81 multiplied by 2,81 divided by 2, close bracket, plus open bracket, 16,833 multiplied by 2,81, close bracket. Now I get my bending moment there on fixed point as 23,612 Newton meter. Now we can go ahead and plot. See, bending moment at A, it is 0. Then bending moment at B, it is 19. Can I write my 19 as somewhere there? 19,332. Then bending moment at C, can I write my 12 as somewhere there? 12,165. Then bending moment at fixed point, it is somewhere there. It is 0. Anyway, then bending moment here, it is 23 on this line here. Let me draw the line. Where's my icons? On this line here. But we are not supposed to calculate it. It is a bit higher. It is 23,612. I want to show you that it doesn't make any difference or impact there. Now, in drawing your bending moment graph, it will be from this point, negative 0.002. It will be just from this point. You draw a straight line. Since there's no UDL, you draw a straight line from this point to that point. Now, if we want to connect to that point there, then from this point to that point, we will then draw a curved line like to indicate that there's a UDL. This is how you draw your bending moment on this cantilever there. But this point was not necessary because we know that the maximum bending moment, it is at what? At the fixed point. This one, you can tell it occurs within point A and B. This is how you draw your cantilever, good people. This is how you draw your shear force and the bending moment and the calculations there. Now let's look at the last cantilever there. I hope this is helping. Now, if you are having a cantilever like this, the first thing that you need to do is to convert the UDL into a concentrated load. It will be 3 multiplied by 4. Then you put it at the center of this. Then it will be 1.5. Now it is 4 multiplied by 3. It gives us 12. That means here it is 12 kilonewton or Newton. Then it's 1.5, the center 1.5. Then here as well, it will be 2 multiplied by 3. Our answer would be 6. Then you put it at the center, 1.5, 1.5. Then you are having 6 Newton. Now, we don't have any other reactional support beside the one on the fixed point. Now, in determining the value of that force on the fixed point, it will be sum of the upward forces equals to sum of the downward forces. Now the only upward force we have is the F fixed equals to downward forces. It is 12 plus 6 plus another 6. Which 6? This 6 and that 6 that we have converted from the UDL. Then our answer, it is 24 Newton. Now here we are having the 24 Newton force. Then our beam, it is what? It is balance. We can then go ahead and draw the shear force and the bending moment. We know that in all given forces, we draw the vertical straight line. This is easy. You see, if necessary, calculate, but here it was not necessary. Where the UDL starts and ends as well, you draw the vertical straight line. The given force at D at C, draw vertical straight line. Where the UDL starts, we draw the vertical straight line. Where it ends, we draw the vertical straight line. Then we can represent our beam as a horizontal straight line. Now, whether we started at the fixed point or free end, it doesn't matter. Now, at the fixed point, or let's start it at the fixed point, or even if we started at the at the free end. If you started at the free end, then you will have something like this, because here you are having a downward force, and since well it is the UDL, it will be from 0 to that point, and that point there, it is what? It is 6. Okay, if we started on the free end. Now between point B and C, there's nothing. We will draw it as what? As a straight line. All right. Then at point C, we are having a downward force. Then it will be -6 and -6. Then it gives us -12. I'll write my -12 somewhere there. Then between this line and that line, there's nothing. Then I will represent that force as a straight line. Right. Now we are having -6 here. Straight line, -12 there. Straight line. Then we are having an extra load on top of the beam. Now let's write values so that people, they don't get confused. Let's write values so that people, they don't get confused before I continue. Now we are having a -6 here. It is this force there. Then we represented that force as a straight line. Then we have negative on this line. We are having a downward force. It will be -6 plus -6. Then we are having -12 there. How did you get it? -6 plus -6. Then we get -12 there. Then we will represent that force as a straight line. That means on this point you are having -12. Now -12 plus -12. Now remember, it's a UDL. We will draw it as a diagonal line. That means on this point we are having -24. Now on this line we are having an upward force, and all forces going up, they are positive. Now you can tell that we are having -12 minus plus 24, then equals to what? To 0. Hence we started at 0. We ended at 0. This is how your shear force diagram will look like if you started at what? At the free end. Then in calculating the bending moment, you will start at A. Bending moment at A, it is 0. Bending moment at B, you work towards the fixed point. Bending moment at B, it will be -6 multiplied by 1.5. Then you get your bending moment there. 6 times 1.5 equals to 9. Equals to -9. Then bending moment at C, bending moment here, it will be -6 multiplied by perpendicular distance would be 2.5. Then you get your answer as -6 multiplied by 2.5 as -15 Newton meter. Then bending moment at D, it will be -6 multiplied by perpendicular distance would be 2 plus -6 multiplied by perpendicular distance from here to there, it is 4.5. Then you get your answer as -39. Got my answer as -39 Newton meter, obviously the SI unit. Then bending moment at E, the fixed point, it will be -12 multiplied by 1.5 plus -6 multiplied by 5 perpendicular distance plus -6 multiplied by 5, 6, 7.5 perpendicular distance at 7.5. Then I get my answer as -12 multiplied by 1.5 plus -6 multiplied by 5 plus bracket -6 multiplied by 7.5. Now I get my answer as -93 Newton meter. That's your maximum bending moment. Now in drawing your maximum bending moment, you can tell you need to start at 0 and end at 0. It will be there at the bottom. Bending moment at E, it is 93 Newton per meter. Then bending moment at D, can I represent it there as -39. Then bending moment at C, it is somewhere there, it is 15, -15. Bending moment at B, it is -9. Then bending moment at A, it is 0. You can tell, but the fact that between E and D there's a uniformly distributed load, then you will write it as a curved line, like, okay. Then from point D to C, you will write it as a straight line. Then from C to B, you will write it as a straight line. Then between B and A, there's a uniformly distributed load, then you will write it as a curved line. Boom. This is how your bending moment should look like on this cantilever. Thank you, good people. I hope this helps and it makes sense.